All right, 5.3 is the last section we're going to do for chapter 5. There are some more in the book, but we'll stop at that. Additional properties of the binomial distribution. We're going to graph a binomial distribution, which is really a histogram, where R is going to be the horizontal axis. The probability of each event is going to be on the vertical axis. And we're going to construct the bars by extending R by minus 0.5 and a plus 0.5. I'll talk to you a little bit on the next slide as to why that is. The outcomes for 0 trials would be 0 success, 1 success, 2 success, 3 success, 4 success. So that's going to be on your x-axis. What's going to happen is that's going to be smack dab in the middle of each of these bars. Okay, so to get the actual number that's on the x-axis, like the x value, it's going to be halfway between. So there's your 0.5. Or your 1.5, or 2.5, 3.5, and then 4.5. Your probabilities, which I just went to the table, found those, and that's how I got those 4 answers, are going to be the heights of your histogram. Okay? Where that's going to help us out is this bar is worth this much, that's your probability, that's your probability, that's your probability, that's your probability. Area underneath the curve will make a little bit more sense as we get to the next chapter and so on. Okay, the balancing point of the distribution, or the mean, the middle, is got a little bit different, unique formula to it. It's now n times p for your mean. So n is the number of trials, and I've got all of what those mean on the slide here. Your standard deviation is going to be the square root of npq. Yeah. So that in practice would be that concept. Let's say I take a coin and I toss it 4 times. So n is equal to 4. The probability of success of getting a heads to appear is 0.5. So half of 4 is 2. The standard deviation of that would be very similar, but now I'm going to take that answer of 4 times 0.5, multiply it by another 0.5 because of q, and then take the square root, and I get a standard deviation of 1. Okay, a lot different than finding the sum of all your x times p's. Okay, so going back to that sharpshooter problem, let's say that sharpshooter is still taking 8 shots times a 0.7, and that's going to work out to be 5.6. I know it's not an exact value, but you could maybe round and say that she hits it 6 times if you want to think of it that way. But 0.5 is just an average, or expected average. That standard deviation is going to be that 5.6 multiplied by what the failure was, or 0.3, and then take the square root. I get about 1.3 for that. Okay. This only works though if it's a binomial situation. Okay. Quota problems, it's the minimum number of trials for a given probability, solved using the binomial probability distribution. We use the binomial distribution table to work backwards to find the number of trials. So we're looking for n. In this case, we actually know what the probability of success of each outcome is. We know how many successes there were. We actually know the answer to the problem. We want to work our way backwards to figure out what, again, that n value is going to be. Okay. Now, the concept that you really have to know is kind of this equivalent formula idea. And the idea comes up from the fact that, let's say I have n is equal to 4 possible outcomes, or 4 trials. My 5 possible outcomes are 0, 1, 2, I'm going to run out of room, but 3, and 4. And what those 5 outcomes need to add up to be equal to is 1. So if I wanted at least 1, which would be 5, 6, or 1, 2, 3, and 4, I could add up those 4 values, or I could go take away this from both sides and go 1 minus the probability of 0 successes. So where it helps out is if we don't know what n is, have no clue, which would be difficult to do this situation because n could be anything it wants and go on forever. I'm trying to develop a pattern here that at least 1 is 1 minus 0 successes. At least 2 is 1 minus 0 and 1. at least 3 is 1 minus 0, 1, and 2. So at least M is 0, 1, 2, 3, 4, 1 below whatever number I'm given there. A certain information service is in the business of finding addresses for a long lost friend. They claim to have a 60% success rate. Okay, so P is 0.6. Success is finding an address. They do that 60% of the time. Suppose that you have the names of some friends for whom you have no address and decide to use the company to track them. How many names would it take to have submitted so you're 90% sure that you got at least 3 addresses found? Okay, so this second percent is a little bit, I don't know, I guess maybe confusing because it's the second percentage we found, but that's the answer that we're looking for. Okay, we're looking for the probability that R is bigger than that. And since 3 is my at least, I got everything below that up until 3. So 0, 1, 2. This equation has got to be basically working out to be bigger than 0.9. So 1 minus, and I kind of think of it this way, 3 numbers of R that will add up to be equal to 0.10. Because 1 minus 0.10 is going to give me 90%. So what I used is the table backwards. And I'm looking for a grouping of n is equal to something that would give me 3 numbers in the 60% column that will add up as close as possible to 0.9 or 0.10. Because I want 1 minus 0.10 to work out to be something bigger than that 90%. Okay. In this case, it ends up being 7. Now, this is one thing that I know is going to take a lot of detail and a lot of practice, so kind of at least want you to hear this, see this, whatnot. We'll come back to class tomorrow. We'll practice this a lot more, but quota problems are things that kind of get missed and overlooked, and I don't want you to overlook them. Here's the assignment again. I would look at maybe all the other ones leading up to the quotas, maybe even look through the quotas, see if they make sense, but we'll practice these for sure.